Let's begin the revision of atoms. This is our 12th chapter. It is relatively easy. Okay, this chapter is relatively easy or easier than our previous chapters from electromagnetism. So you can put this at par with optics, the chapter on optics. And another good thing about this chapter is that you already know a few things about atoms, like what are its constituents and all. Okay, so we are going to begin our revision by recalling different atomic models that we discuss in this chapter. There are three atomic models that we discuss. The first one is the plum-pudding model due to Thomson, then the planetary model due to Rutherford, and then its modified version, and we call it the Bohr's atomic model. And after that, which the model that we have not studied, that is based on the rules of quantum physics. So what is the basis, or what does the plum pudding model tell us? Plum pudding model tells us that atom is actually a ball-like structure where positively charged is distributed uniformly throughout. Okay, and then because or to maintain the electrical neutrality of atoms, the electrons, can't say electrons, but negative charges, they are embedded like plums in the pudding, hence the name plum pudding model. This model could explain the formation of ionic compounds and all. Okay, it could explain formation of ionic compounds, the electrical neutrality of atoms, and it was stable. Okay, according to plum pudding model, an atom is a stable species. But what led to rejection of the plum pudding model? The experiments with alpha particles and the gold foils, or metal foils, thin metal foils, which were carried out by Rutherford and his colleagues or students. So what were the main conclusions of Rutherford's atomic model? The main conclusions were that almost all of the alpha particles they emerged out of the thin gold foil without any appreciable deflection, but very few of them suffered a very large deflection, and that deflection was very much comparable to a head-on collision. So let us say this is the nucleus or the atom, then the alpha particle came and it underwent this head-on collision, and it just returned back like collision of a ball with a ball. So these observations allowed Rutherford to not only conclude that atom is mostly empty, but it also allowed him to estimate the size of the atom and the concentrated location within the atom, which he called the nucleus, and its size. Okay, so on the right side we can see the two figures. If we imagine the plum pudding model, okay, then the alpha particle, which we know is positively charged, okay, it should undergo only a small deflection. An alpha particle is scattered through only a small angle. Correct? So this small angle is different from almost undeflected. Almost undeflected means extremely small angle, but here, because it is spread throughout, it should undergo only a small deflection. But what did Rutherford's observation confirm? Rutherford's observations confirmed that there is a possibility that alpha particles or an alpha particle may get scattered through a large angle. So please note the difference. Plum pudding model of J.J. Thomson does not predict this large angle or large deflection. Okay, so this led Rutherford to think that okay, atom might be mostly empty, unlike plum pudding model, but most of its, or rather all of its positive charge is concentrated at a tiny location, which he called the nucleus. Is that clear? Yes. Now we also have some graphs. Acha, before we go to that, let's quickly discuss the Bohr's atomic model. We'll come back to this. So what was the main point, okay, the main no point we can say, which Rutherford's planetary model had. You can say its drawback, and that drawback is that according to Maxwell's electromagnetic theory, if you have an accelerated charge or a charge which is accelerating, an accelerating charge, it should emit electromagnetic radiation. Okay, it should emit electromagnetic radiation. And Rutherford suggested that although his calculations about the size of the nucleus and overall structure of atom was right, he said that electrons revolve around the nucleus, and we know that if any charged particle undergoes even uniform circular motion, because its velocity keeps on changing, it has centripetal acceleration, so it must emit electromagnetic radiation and ultimately fall in the nucleus. So this was the drawback of Rutherford's model, because it was inherently unstable. But that doesn't happen, or rather that is not observed. So Niels Bohr was convinced about the validity of the Rutherford's model, so he carried it further. He kept the basic structure same, but he then introduced 3 postulates. And in Bohr's postulates we see the unison or the confluence of classic ideas from classical physics and ideas from quantum physics. We will revisit Bohr's postulates in a while. Returning to Rutherford's experiment, these were the observations. The main observation was that almost 99.86%, okay, 99.86% of all the alpha particles which he bombarded against the gold foil, they had scattering angle of less than 1 degree. Only 0.14% could be deflected with a deflection angle of greater than a degree. And the number of alpha particles which underwent or which suffered a deflection of greater than 90 degrees, they were only 0.0125%. These are the reasons why he concluded that atom is mostly empty, but still its positive charge, it's concentrated at an extremely tiny region within the atom, which he called the nucleus. So this graph is actually the confirmation, or rather the observation from which he concluded the things. And you can see that here on y-axis the scale is exponential, okay, or you can say logarithmic, rather logarithmic scale. So 2, 3, 4, 5, 6, and this is 10 raised to 1, right? And you can see the reverse exponential nature here, the negative exponential nature. So as you increase the scattering angle, the number of scattered alpha particles drops drastically. So 10 raised to 7 is here, then somewhere between 10 raised to 5 and 10 raised to 6 is here, and then somewhere above 10,000 is here, and so on. So these are indicators that alpha particles do not actually feel the repulsion of the atom, or the positive charge from the atom, and they just go and deflect. Okay. Okay, so what were the calculations of Rutherford, or what did the Rutherford's calculations suggest? They suggested that size of the atom, or atomic radius, you can say atomic size, is of the order of 10 raised to negative 10 meter, and within that, much smaller than that, around 10,000 times smaller than the atomic size, is a very tiny thing called nucleus. So this is the size of the nucleus, around 10 raised to negative 15 to 10 raised to negative 14 meter. We don't have the calculations even in our theory part, so we'll just note the numbers. And these estimations were or are right. Now let's move on to atomic spectra. We have seen that atomic spectra are of 2 types. We can have emission spectrum and we can have absorption spectrum. So this is basically when you excite the atoms by an incoming electromagnetic radiation, the electrons jump to higher energy levels, and when they return to their ground states, they emit electromagnetic radiation of appropriate frequency. That is what we call an emission spectrum. And in this chapter, we have emission spectrum of hydrogen atoms or hydrogen atom in detail. But if you remember, during our regular lectures, I had shown you the emission spectra of almost all atoms. I even told you the website to visit. Okay, and what we find is these atomic spectra are not only there in the visible region. Because now we have studied electromagnetic radiation and the Maxwell's rainbow, we know that there exist electromagnetic waves to or on either side of the visible region. If we increase the frequency, then you go towards ultraviolet and that part, and if you decrease the frequency, increase the wavelength, then you see infrared and then radio waves and so on. So atomic spectra act as signature of the atoms, okay, signature of the elements, we can say. Now, what was lacking a theoretical explanation was the spectrum of hydrogen in the visible range. It had some colored lines in the visible range, and this was named as Balmer series. This series of lines is named as Balmer series. Okay. So this fellow, he was a teacher in a school. He wrote a paper in which he gave this empirical formula. He gave this empirical formula. What did this formula give? This formula gave the correct values of these lines, alpha line, beta line, gamma line, and so on, okay, delta line and so on. So here we can see the decrease in the wavelengths in this direction. It's 656 nanometers here to 364.6 nanometers here. Okay, so Balmer said, let us substitute n as 3, 4, 5, 6 and so on to get these lines 3, 4, 5, 6, 7 and so on. Correct? The first line or the line with the largest wavelength is always called as the alpha line. So this was the Balmer series, and he said, okay, the spectrum of hydrogen consists of these lines whose wavelengths are given by this. And please note, here we have 1 upon lambda on LHS. So this constant here, which we have called Rydberg's constant, its dimensions must be that of reciprocal of length, and its value is 1.097 into 10 raised to 7 per meter. And later on, when people came to know about the whole electromagnetic spectrum, then they found that the emission spectrum of hydrogen is not only present in the visible range, it is also present on either side of it, that is in the infrared region as well as in the ultraviolet region. Okay, so we have these lines, the Lyman series, Paschen series, Brackett series, Fund series and Humphrey series. We did discuss it. Then we have this Humphrey series also. Correct? The Lyman series is in the UV range, and all the remaining are in the infrared. Okay, infrared, and so on. And what was striking was that if we changed this 2 to 1, 3, 4, 5, 6 and so on, then we were getting these lines in these series, the Lyman series for n equal to 1, Paschen 3, Brackett 4 and so on. Okay, so this was an indicator of quantization. This was an indication of quantization of energy levels. We very well know or understand what quantization means. We have talked about quantization in two contexts. We have talked about quantization of charge right at the beginning of this course, and we have also talked about quantization of energy. We have called that energy bundle as photon when we explained the photoelectric effect. And this is also a clear indicator that the energy levels are quantized, but we didn't have at that time the correct theoretical explanation to that, which was given by Niels Bohr. Okay, yes. So what was Bohr's dilemma? Bohr actually went to Rutherford's laboratory and he stayed there for about a month, and he was very much convinced that the Rutherford's model is correct. But then the scientist in him was he kept asking questions. If the model is right, then why it is unstable? Okay, why are the atoms stable and the model unstable? Because accelerating charges should or must emit electromagnetic radiation, and they should lose energy, and the electrons or the negatively charged particles, they should spiral towards the nucleus, and that didn't happen. That was his dilemma. So to resolve it, he proposed three postulates. So these postulates, using these postulates, he was able to explain the atomic spectrum of hydrogen, not only in the visible region but also on the in the infrared as well as in the ultraviolet region. So he basically gave theoretical explanation to this particular formula, and the Rydberg's constant, we know now on what values it depends. It depends on the permittivity of free space, it depends on charge and mass of electrons, it depends on Planck's constant, and so on. Correct? Okay. So what were his postulates? Let me again highlight this, that Bohr's model is essentially a modification of planetary model. Please remember that. Okay, so he kept the basic structure same, the nucleus and the electrons revolving, and this is contrary to this jump from plum pudding model to planetary model. In the plum pudding model, the positive charge is spread everywhere, but in planetary model it is not, and Bohr kept that the same idea in his postulates. Okay, so in his postulates we can see the confluence of the classical concepts of physics and also early quantum concepts. Quantum comes from quantization. So please remember these three postulates. You have to, I'm sure there will be a question in your exam either on the Bohr model or on energy calculation or on hydrogen spectrum, or even a formula, a simple formula. Okay, so what were his postulates? Number one, an electron in an atom could revolve in certain stable orbits. The electron could revolve in only certain stable orbits, and if the electron is in those stable orbits, then it doesn't emit any electromagnetic radiation, it doesn't emit energy. Correct? So this is called as postulate of stationary states. Stationary refers to stable. Stationary refers to stable. So this is not a mathematical statement. Okay, here he talks about, he says, okay, there are some stable orbits which exist, and if electron is there in that orbit, then it is not going to emit any energy. Number two, we call this as the postulate of defining stable states. The electron revolves around the nucleus only in those orbits where the angular momentum is some integral multiple of h upon 2 pi. So this is a mathematical statement. He is saying that the angular momentum of the electron, mass of electron, velocity of electron or speed of electron in that particular orbit, let's call it Vn, nth orbit, and stable orbit, into Rn, which is the radius. He said this is equal to, this is quantized. He didn't say energy is quantized, but he's saying angular momentum is quantized. Okay, how do we define angular momentum? Vectorially r bar cross p bar. Okay, in usual notations where p bar is mv bar, the linear momentum. If you have studied rotational dynamics or rotational motion, you will understand what I'm talking about. And because we have electrons revolving, it refers to rotational motion, angular momentum has to be there. Okay, so this is quantized. He said this has to be an integral multiple of h upon 2 pi, and in our previous chapter we have seen that the quantity h upon 2 pi, we write it as h and then we put a bar here. Correct? So this is a mathematical equation. And now Bohr went one step ahead and said, when electron makes a transition from a higher energy level to a lower energy level, it emits a photon of appropriate frequency. Okay, that's our third equation, postulate. An electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted, having energy equal to the energy difference between the initial and final states. And we know from our photoelectric effect discussion that photon's energy is directly proportional to its frequency. Correct? And what is the constant of proportionality there? That is the Planck's constant. So the energy of the photon that comes out, that is emitted by the atom, is actually the energy difference between the initial and the final energy levels. Now, who sends the electrons into higher energy orbits? We don't say anything about that here, but obviously we excite the atoms. That's why the electrons go to higher energy levels. So here, because he said that it is delta E upon H, we can say that here we see the incorporation of the Planck's quantum concepts, and we also add Einstein's name here because he has explained photoelectric effect using the Planck's quantum theory of light. Okay, now let's see the expressions for the radius of the nth stable orbit, the speed of electron in the nth stable orbit, and the energy of the electron in the nth stable orbit using Bohr's postulates. Let me tell you that here we have used one more formula which I have not written here, and that is the centripetal force me Vn squared upon Rn is actually the Coulomb force, 1 upon 4 pi epsilon naught E ZE, assuming that there are multiple protons in the nucleus, upon Rn squared. This is one equation. There are two unknowns here, Vn and Rn, and what is the other equation which has Vn and Rn? It is this one. So the force thing, the centripetal force is the Coulomb force, and the quantization of angular momentum. If you know these two, then you can get everything. Okay, then you can get the expression for Rn, then you can get the expression for Vn. Now why I am saying this? Because both these equations contain two unknowns, the radius of the nth stable orbit Rn and the speed of electron in that stable orbit Vn. Correct? Two equations, two unknowns. You can easily calculate this. I just want to go through these ones. Remember, Rn is directly proportional to square of n. Rn is directly proportional to square of n, and Vn is inversely proportional to n. So as n increases, the speed decreases according to Niels Bohr's postulates and calculations. Note that Rn depends on permittivity, Planck's constant, charge on electron, mass of electron, and also the atomic number or the number of protons in the nucleus. And if I substitute n equal to 1, then we get the radius of the first stable orbit, which is found to be 0.05306 nanometers. Nano means 10 raised to negative 9. In your book, R1 has been referred to as A naught. Okay, the speed Vn depends on charge, depends on permittivity, depends on Planck's constant, and of course the atomic number. Now what about energy? Remember, this energy here, En, consists of two things. Because Vn is non-zero, the atom has kinetic energy given by half mVn squared or MEVn squared. And because the electron and the nucleus, they form a system of charges, it also has potential energy with a negative sign. Okay, Pen and Ken. And the formula for this potential energy, you will find it in our second chapter, electric potential, that is the first part, and capacitance. If you remember that, we have done a derivation in which we have used the fact that the Coulomb force is a conservative force, and this En is an addition of Ken plus Pen. So if you do that, use the formula, put everything and add, then you will finally get En to be negative z squared upon n squared into 13.6 electron volt. Electron volt is a much smaller unit of energy. We have already discussed that, so I will not go again in that particular thing. Okay, and for hydrogen atom, Z is equal to 1. Z is equal to 1 because there is only one proton. For deuterium and tritium also there are only one. There is only one proton, but let's say for helium ion or doubly ionized lithium ion, Z will be different, and Z will be 2 and 3 respectively. Okay, and then if you take the energy difference between two levels, let's say En minus En, then the constant that you get, okay, then the constant that you get is this one, okay, Z squared e raised to 4 mass of electron upon 8 into Planck's constant cube into speed of light and vacuum into epsilon naught squared permittivity squared. I will suggest you to memorize this. I'm not saying it is required, but you might want to know which power of charge on electron is there in Rydberg's constant. So the experimentally observed value and the theoretically calculated value of Rydberg's constant matched, so that automatically explained everything which was previously unclear about the atomic spectrum of hydrogen. Now, so we can see the energy levels of electron inside hydrogen atom. This is clearly quantization, correct? You cannot have an electron in its stable position in between n equal to 1 and n equal to 2. Okay, so these are stable energy states, clearly indicating the quantization. Okay, can anybody tell me why does a negative sign exist here? Can anybody explain why do we have the negative sign here? Yes? Yes, because this is, yeah, you're right. Because this total energy has two components, as I said earlier. It's potential energy and it's kinetic energy. For kinetic energy, it's okay. It's always non-negative. But what about potential energy? We had assumed that potential energy, or rather we usually assume that potential energy, electric potential energy, is zero when your charge is at infinity. Okay? And because you bring it from infinity to that location, your potential energy in this case is negative. Okay, and negative also means you have to supply the energy to make it free. And what's the minimum amount of energy that you need to spend on it? That's 13.6, also called as binding energy or ionization energy, correct? And the energy difference between the two, okay, let's say the electron jumps from n equal to 2 to n equal to 1, then whatever the energy difference is, if you divide it by Planck's constant, you'll get the frequency of the emitted photon. Okay, and then what does this indicate? This indicates that the electron has not only become free from the electric attraction of its nucleus, but also has some additional energy, that is the unbound or ionized atom. Okay. Now, what is the explanation to the spectral lines? Okay, what is the explanation to the spectral lines? Here we talk about Balmer series only, because other series can be very easily explained if you understand what Balmer series tells us. Okay, so in Balmer series, the electron is still, rather, when the electron returns to a more stable state, it is not the most stable state. The most stable state is the ground state. Okay, but because historically Balmer series was known earlier than, or it became known earlier than the Lyman and the other series, we talk about Balmer series here. So here the electron from third, fourth, fifth, sixth, and so on orbits returns to the second stable orbit, and that second is important. N equal to 2 is important. That's the reason the empirical formula given by Balmer has n equal to 2 in the first term's denominator. Okay, this 2 here, this 2 is because it returns to the visible spectrum, n equal to 2, second orbit, second stable orbit. But the electron can very well return to the first. In that case, you get the Lyman series. So these arrows here refer to, or the number here, it does not refer to the electron, the orbit of the electron where it was initially. It refers to when it will go finally. Okay, so those things here in the table which I showed you here, where is it? Yes, in this table, these numbers 1 squared, 3 squared, 4 squared, 5 squared, these refer to the returning orbit number or returning energy state number of the electrons. In Balmer series it is 2. Correct? Alright. So that explains the hydrogen spectrum, well, most of it by Bohr model, where we use a third postulate, delta E, or change in the energy levels or energy differences, h into nu, nu is the frequency, h is the Planck's constant. हे समझ का? Okay. Okay. Now Bohr was unable to explain his postulate. Why should angular momentum be quantized? There was no explanation to that, although that assumption explained everything nicely. So here we go to our previous chapter, dual nature of radiation and matter, symmetry arguments, and the de Broglie hypothesis. De Broglie hypothesis. De Broglie said, okay, if electromagnetic radiation exhibits particle characteristics, matter should or may exhibit wave-like characteristics. Okay, so the wave nature is very much evident here, and we now consider an electron as a standing wave pattern. We now consider electron as a standing wave pattern. If you remember, in 11th standard we had a chapter on this, stationary waves or standing waves, where only those standing waves are sustained, be it an air column closed at one end or an air column open at both the ends, where the wavelengths are a fixed multiples of a number or fixed multiples of the length of the pipe, you know that. So that clearly indicates the quantization of wavelength. And he said, okay, this is an analogy. According to de Broglie, these are standing wave patterns along a line. You can similarly have standing waves along a spherical surface. But please note that this surface is not like that of any percussion instrument. Okay, this is actually electron exhibiting that wave-like characteristics. Correct? Okay, so de Broglie said, okay, well, let's use this standing wave pattern condition, or only the sustained standing waves, and for that he said 2 pi Rn has to be an integral multiple of lambda. Okay, so here this is analogous to the length here. This is analogous to the length here. So it has to be an integral multiple of wavelength. What is 2 pi Rn? The circumference. The circumference of the nth stable orbit. That is equal to n into lambda. Second formula is from the de Broglie hypothesis is what? This. Lambda is equal to h by p. The wavelength of a material particle is given by Planck's constant divided by mass into velocity. Now don't see the wavelength or wave-like nature of particles of our size. That's because of an extremely small value of Planck's constant. It's 10 raised to negative 34. So no matter how fast you go, your wavelength will always be small, except in those situations where mass is very small. Okay, where mass is very small, like electrons. So there you can see the wavelength and the wave-like characteristics. So if you merge these two formulae together, meaning if you substitute lambda as h by p here and readjust the terms, you'll get the angular momentum as nh upon 2 pi. Correct? You'll get the angular momentum as nh upon 2 pi. You can easily see that. You write here lambda as h upon mv, shift mv there, you'll get everything, get 2 pi here. So it will be nh upon 2 pi. Correct? So this is Bohr's, this is de Broglie's explanation to Niels Bohr's postulate of quantization of angular momentum. Last part. Is Bohr's model the complete description? No. So what are the limitations? First thing is that it is applicable only to hydrogenic atoms. What does that mean? Hydrogenic atoms mean the atoms which have only one electron or atomic species. So this can be hydrogen, singly ionized helium, not alpha particle because it doesn't have any electron, singly or positively charged helium ion, just one electron gone, one electron is still there. And then for lithium, whose atomic number is 3, let's remove 2 of its electrons. So only those hydrogenic species, they satisfy, or Niels Bohr or Bohr's model explains these things. So what happens to multi-electron models? In multi-electron models, we are also required to take into consideration the electrostatic or electric repulsion between electrons. For a Bohr model, we don't consider that because there is only one electron. Correct? The second limitation is that the lines, the spectral lines, are of different intensities. Okay, the spectral lines in any series, let's say in Balmer series, visible region, Balmer series, have different intensities. So all lines are not equally bright. Bohr model also didn't have any explanation to the different intensities or the existence of lines of different intensities. Correct? So that completes our revision of atoms. If you have any doubts or if you want any further clarifications, you can ask me now.